In this video, we are going to talk about DDR memories, and we will start with something super interesting, and that's how to measure them, how to test them. And then also we will talk a little bit more about signals, how memories work. So this video is going to be for everyone who would like to understand a little bit better how to design systems with DDR memories. Correct, Randy?
That's right. Yep.
Okay, so let's do it. Show everyone what is behind you.
Okay. This is my this is my toy room. I have the lab that I work in. We have a number of pieces of equipment. On the right, this is a bit error rate tester, and we can calibrate and program very specific types of stressed signals, right? Worst case conditions that you might observe in a real system. Jitter, crosstalk noise. So that's what this is. In the middle, we have a typical motherboard gaming system, processor and DDR5 memory, of course. And I think later on we'll show how we do in-system tests. So the system is running, it's booted, it's reading and writing data. And so we'll show how to test that.
So
and
we
then
have
on my
probes connected to the memory modules, and we will measure the signals running to the memories, correct?
That's right.
Okay.
We have 3 probes connected. These are soldering probes. So you have to be able to get access to the signals of interest, solder them in, and my eyes are not good enough, even though I got really strong glasses. Now you have to have a microscope. The pitch is really small. So yeah, you solder them in, and then that allows you to observe the signals that are going back and forth between the processor and memory.
And we will talk about how we can solder probes, because I know when someone designs their own board, very often they would like to know how to measure this kind of signal. So we will talk about this.
Yep, exactly. I used to solder probes many years ago. And like I said, my eyes are not that great. And so Keysight and a number of other test equipment companies, they usually publish soldering guidelines, and it's very very scientific. Getting the temperature just right, pre-baking the PCB, things like that, to make sure you have a reliable connection.
Okay, and then I interrupted you. The next one is the scope.
Oh yeah, exactly. So the next setup here on the left is an oscilloscope. This is a larger high bandwidth oscilloscope. So whatever DDR speed you're working on, we typically have a rule of thumb we call 5 times rule, or fifth harmonic. So you take the data rate, divide by 2 to get the fundamental frequency. And here we're running 4.8 gigahertz or 4.8 gigabit DDR5 speed. So the clock rate is 2.4 gigahertz, and multiply that by 5. You know, that's about 12 gigahertz approximately. And so we would recommend the oscilloscope bandwidth that you use to do the measurements should be, you know, approximately 12 gigahertz for this setup. You could use more or less depending upon your budget and other needs.
Okay, so let's have a closer look. I think you can move the camera you mentioned.
Yep. Okay. All right, here we go. Let's see if we can get this to work. So yeah, it's very nice to not just see things at a glance, but we will get a more in-depth view of how this works and what this looks like.
Okay, about the device, what you have on the right, if I understood correctly, so that device is to measure memory chips, or it's like it emulates the controller? Yeah, this one.
That's right, yeah.
Okay.
So here you have, on the front panel, you have this yellow section. This is a channel. So we have data out, plus and minus, data in. So output, input. So we're sending a test signal out and then somehow the device is in a loop back state. It literally loops back whatever signal it detects, and the signal has to be latched as if this is the real signal that was received and detected and sent into the internal core. That signal instead, for testing purposes, is looped back, and then it goes back into this data input. So out, in, and the fundamental test here is the bit error rate or bit error ratio test.
Okay, and the big board on the table,
Yeah, this one
is basically used to probe all the pins on the memory chip or something?
exactly. Look at all the rows and rows of coaxial connectors here. So as you know, memory, 64-bit bus, multiple DQS strobe lines. We have the clock. We have different sideband channels and auxiliary lines like alert, reset. So we break out all those signals here, and that allows us to more precisely, in a controlled manner, inject and also measure. And so, there's connectors on the front and even on the back.
Where you plug this in? I see there is connect.
Yeah, I could plug this into a motherboard itself or a special fixture. So this is one type. This is an RDIMM parametric test fixture.
Okay, so this is not for measuring the memory chips. This is kind of, you measure the controller.
I measure the controller, the memory controller, or possibly the system.
PCB layout and the connector and everything together.
Yep. Another fixture is what we call a replica card, and this, like the name sounds, it's replicating or duplicating or emulating a raw card. A raw card is the reference memory module design file, and you can download these from JEDEC. If you want to see what a UDIMM schematic or layout for a 2-rank or a single rank, these are publicly available. You can register at jedec.org, download these files, and then review the design to see how it's laid out.
I recommend this. Yeah, I recommend this, especially when people ask me about some specific questions about memory layout or memory modules. I always recommend them go to JEDEC website. You can download all the reference designs. You can measure the length. You can see how they routed it and all those things. They can learn a lot from this reference design.
Yeah. And I actually, what I do is I do exactly what you just said. Whenever I'm preparing for a test, I want to say, okay, which DQ line do I want to focus on? Which is the worst case net? Well, I'm going to go look at the layout file and determine, well, this one, the length from the Goldfinger to the BGA, this is the longest trace and it has the closest proximity. So maybe it's the worst crosstalk. So you have an idea by the design guide, kind of possibly what to expect. But this board is emulating each raw card. This is a E0, this is a C0. And then it's also reversible. D0, A0, etc. So we group these into DQS pairs. So here's the clock and different CA signals. So this is pretty fun. It's getting test and everything that you see here. This is just testing the DRAM in isolation, right? We want to test the interface. We want to test the physical layer. How good is the transmitter performance of just the DRAM by itself, which is why we have these coaxial connectors, right? Very controlled impedances, clean launch, unlike the soldering probes, which is more system level.
Can you test also memory chips itself? Because I heard there may be big differences between chip manufacturers, and maybe for some critical applications you really would like to pick the correct memory chips.
Yeah, in fact, that's a really good point. I think one of the big differences with DDR5, and not a lot of people, unless you work on DRAM specifically daily, you work for Micron or SK Hynix. Maybe you're not aware of this, but DDR5 has now picked up very complex advanced equalization. So the receiver has a way to compensate for PCB losses and ISI,
Mm-hmm.
and its decision feedback equalizer. In order to test that, the way it's, like you said, the way it's implemented could be different from one manufacturer to the other. And so this whole setup allows you to kind of simulate worst case conditions and then check, is the equalizer, is the DFE working properly?
Mm-hmm. So there is another board where you can solder down memory chip?
Yeah, there's another board. Yeah, I don't have that with me at the moment, but it turns out you could actually use a standard DIMM, the other fixture that I don't have at the moment, but you would plug the DIMM into the socket,
Mm-hmm.
and
Okay.
then you would have the same types of
Mm-hmm.
connectors like this, which are then routed
Mm-hmm.
into this test equipment, and then you could test it directly that way.
Okay. And this kind of system can measure DDR5, 4, 3, all the kind of memories, or?
Yeah, it can support the slower speeds, but only DDR5. DDR5 is the only generation that actually requires receiver tests.
Mm-hmm.
So for a DRAM manufacturer to offer the memory, they have to prove that they've passed these tests, and usually they're in the data sheet. Here's the BER data, or here's the way that we train to get the optimum receiver equalization.
Mm-hmm. Okay. Let's have a look on the gaming system. So,
All right.
because this is closer to, like, I don't want to say everyday life of engineer, because not everyone can really measure
More
memories,
typical.
but this is
Yeah.
something closer to like hardware design engineers to see how actually we can measure memories directly on our board. So
Yeah.
this gaming system is using standard uh, slot for standard DIMM module or something.
Yeah. So this is a two DIMM per channel memory. I only have one DIMM uh, connected at the
Mm-hmm.
moment. And this DIMM, it's a standard UDIMM
Mm-hmm.
because unbuffered, right? There's no buffer for any of the signals.
Mm-hmm.
But here's a close up of what the DIMM looks like, the
Mm-hmm.
way that we're testing it. And if you look really closely, let's see if I can get a better view. You see this sandwich fixture? This is a BGA device interposer,
Mm-hmm.
and we have to unsolder the BGA and then put what's called a riser. It's a very small PCB in order to lift the interposer up high enough so it doesn't touch the neighbor DRAM, which
Mm-hmm.
is like what you said earlier. It's
Yeah,
so
I
tight.
didn't know something like this can be done, because I was a little bit worried on many boards what I design. Memory chips are very close to each other. And I was
Yeah,
thinking like, but how I'm going to, I knew I will need interposer to access the signals, but I didn't know how I could fit this interposer when there are chips close to each other. Now I can see how it is done.
yeah. Yeah, so that's this little piece here, and there's pads, uh, soldering pads on the outside here. So that's where we route out, we pick off the signals in between, and then we can. The next step, once you do that, then you come along here, and here's another one. Now we have the
Probes,
the
correct.
probes attached.
It
Um,
doesn't focus correctly.
yeah,
Oh, and now, oh, I can see now. This is cool.
okay, yeah. So I'm here. I want to access clock, chip select. CA, just one of the, there's 14 CA lines. I just want one CA. Of course, data, DQ, and then DQS.
Okay, we will talk about this also a little bit later, but this is very important. So everyone who would like to measure memories, remember what kind of signals we need.
Yeah.
Okay,
Yeah.
perfect.
Let me take a minute and also describe. Okay, I've got the probe attached. The system is running, and I've got 3 probes here. So here's 1, 2, and 3. And I don't know if you could tell, but on the end of the probes, I have these color bands, these rubber bands, and those colors match the signal color on the scope. So whenever you're moving back and forth between the system and the scope, and you want to know, what am I connected to, which signal? It's very common to have these color coded, just so you can track and know which signals you're measuring. But basically, here I will disconnect very carefully here.
Maybe don't touch it.
Okay. No. Okay. Kids, don't do this at home. Okay, here we go. I'm gonna do this live.
Okay.
But basically, this is what it looks like. Two connectors side by side, plus and minus. Of course, the outer barrel is the ground connection, and then this just goes right on here. So that's what it looks like.
So this is like this is the special expensive part of the probe, and the other one is something what you can then replace, or only the
yeah exactly. This part right here, this part that's loose, the bigger part is the amplifier. We call it, it's the probe amplifier. It's basically a buffer. And then this part, which is the passive, I'm going to gently try to put it back. And of course, when you attach this, you always want to be slow and, no coffee in the morning. There, okay. Whew. Make sure there's no good strain relief. So it's just kind of sitting on top of the board. And yeah, everything looks okay.
Okay, and you can always buy these heads, because I guess they can get damaged when you solder and desolder them too often, or you can just change the cable, or how does it work?
Absolutely. Here's an example of one that's loose. Okay, this is the soldering part. Again, we call that the probe head. And like you said, they're modular, meaning you can purchase different types. Some have long extensions, some are short, some are coax. This is a flex. You see, it's a flex cable, so it can fit very, very narrow. And if you have a small gap between the heat sink and the module, so it can fit in between easily. It's very high bandwidth. On the back side here, I know it's hard to see. The signals are routed on this front side, but then if I turn it around, this is a solid ground plane, and it helps with noise immunity and crosstalk. So, and then I was going to say, of course, it's going to be really hard to see, but let's see if we can get a close up of the probe.
Maybe put your hand behind it.
Yeah, let's see if I do this.
No, doesn't focus. Or maybe it's too close. I don't know. Doesn't focus.
Yeah, but this is so small. I can't even see it with my own glasses. But that's the pitch that we have to work with today. And on the very front, there's
now it's focused.
Yeah, there's 102. It's not 0402 resistor component size, but it's the next size below.
0201.
0201 surface mount resistors, the 110 ohms that are used for dampening reflections. When we solder on, there's a discontinuity. So that's our probe head right there. This is kind of loose.
Okay. So now the question is, do we need to run some special software to be able to test memories?
Yeah. Let's change the camera view a little bit, just so you could see what we have here. Okay. Uh, we've been running before, and this software here, this is called MemTest. It's free. In fact, this is so common for specialized custom systems that this is built into the BIOS.
Mm-hmm.
And in fact, just for fun, I'm going to reboot the system right now, and I'll show you how. Sorry about the glare,
Oh, it's okay.
but we'll restart, and I'll show you how you might start this up from a typical system without installing anything or running. We'll hit F1 to go into setup.
I know this memtest, it can be also used on Linux systems and ARM, MIPS, all the kind of different processors. Because it's actually quite a simple thing. No, I think it sends some patterns and it's reading them back and something like this.
Yeah. When you come into the BIOS, you have your typical dashboard view. We could see that there's 8 gig of memory, and it states DDR5 4800 speed. That's the default speed. I've overclocked this. This is really nice. This whole system, I'm not a gamer, but I love the fact that this is tuned and designed to be overclocked, and it works quite well. But for today, the main interest here is we'd like to run memtest. So it says, do you want to activate memtest? Yes. So now it's running the memtest application within within the BIOS. And notice that as it starts, it gives you some diagnostic information, the memory speed, how much cache you have. And the test here, it says test for moving inversions, and it says what address you're testing, the address range, and the actual pattern. So it's just reading and writing traffic.
Okay. And so what kind of signals we would like to probe, and what should we see on our scope by measuring memories?
Now I'm going to switch to, I'll keep the camera view so you can see memtest running. But now
it would be great if you are on the camera. But you can move the camera a little bit to the left so we can see the scope. Okay, so there is the scope, and the screen of the scope is on our desktop. That's what we see on the desktop, and basically you will be using this remote access to the scope, correct?
Yep. So as you can see, memtest is running here on the right, and then the system is probed. I have 3 probes that I'm attached to the scope. So I'll turn on right now defaults. If I do a default setup, right? Default setup. Okay. Channel 1 only is on. So let's turn on channel 2. Okay. So just right off, immediately I see, okay, there's 3 signals. Let's separate these. I probed these. I designed the connection and everything, or I had a technician who's very good at soldering connect this up for me. So I know what signals I want to measure, but let's go ahead and stop this for a minute and just look at what we have here on screen. And I'm also sharing the same on the desktop.
Yeah, I'm looking at the desktop.
Okay, so here we have channel 1. This is
the yellow,
yellow, and that's terminated high, so it's a pull-up type of I/O. This is one of the CA signals, so command address bit 4, or CA4. And that'll be important later on when we go and set up the test. I'll show you. The green channel 2 is our data signal, and it looks a lot like the CA4 signal, but you notice that it's a lot more dense. Okay. Notice that it's more dense
because it's on every edge of the clock, so it's
exactly
kind of
double. That is. We are clocking the data on the rising and falling edge of the clock. but the CA is only on the rising edge.
Mm-hmm.
So that's why there's twice as much information on the data DQ than there is on CA.
Mm-hmm.
Now, the last signal, channel 3, which is blue here on the bottom, which signal do you think this is?
That's differential signal, I guess, because I
That's right,
see
yeah.
the level is in the middle, the 0.
Yep. This is the strobe, DQS. And DRAM, the real name for DRAM is SDRAM, synchronous dynamic random access memory. So the synchronous part is because it's synchronous to the clock, but it's also source synchronous. So there's actually a clock that's coming from the source matched to the data, so that we have DQS strobe, DQ data, and CA4 command address.
Okay.
Yeah.
So these
Now,
are the signals what we may need if we would like to measure memory. So what can we measure?
Yeah. Okay. So not everybody needs to do this low-level view of, I mean, this is like the low-level electrical view of these high-speed signals. Most of the people can just run mem test and say, yeah, it looks good, it passes. That's considered a functional test. But if your job is to design the PCB, design this, write the software, or if you're interacting, creating a memory design at the low level, you really do care about the performance at this level, with this view.
Mm-hmm.
So one of the first things that, if somebody sits down to go measure the system, one of the first things that they have to do is they have to understand, well, one thing about the setup is that the way we're measuring, because we're measuring in system, we get the read data and the write data at the same time. Remember, the data bus is bidirectional.
Yes.
So data starts at the host, the memory controller. It gets written to the memory, and then at some point later on, the controller says, hey, remember that data I wrote to address XYZ? Please send that back. So it's reading and writing data constantly, back and forth, back and forth. But if you look at the screen, can you tell which, the data is the green signal in the middle? Can you tell which one is the read or the write data?
I would say there will be difference how strong the signal is, maybe.
Yeah. Yep, that's true.
So maybe I can see some of them are a little bit smaller, some of them are a little bit bigger. So
exactly.
Some of them will be coming from the controller and the other from the memory chip.
Wow, you have really good eyes. In fact, I would say, see this burst here?
Yeah.
This burst is maybe a little bit lower in voltage than this one.
Yeah, that's what I noticed. Yeah.
Yeah. So the way that I'm probing closer to the DRAM because I have that interposer, that special fixture. Therefore, you could, in theory, I would say the larger amplitude signal, part of the signal, is the read cycle. And then the smaller signal that went all through the PCB, through the via transitions and connector, it has some signal degradation. It's a little bit smaller. So I would attribute this to the write cycle.
Mm-hmm.
Okay.
But we may need to confirm this, correct? Because maybe
exactly, yeah.
But the voltage should be same for processor and also for memories. Then theoretically, and it may depends also maybe on termination or something. So we should confirm this, I guess.
Yeah, in fact, I want to show you. This is not part of the test, but can I show you what the signals look like when the training happens, when the system first starts up?
Okay. Yeah, I'm curious.
Yeah,
because
this is really cool.
We would like to talk about this too, because that's important part of using memories in system to train them.
Yeah. So do you see how the signals look like right now?
Yes.
They're very uniform. It's a kind of a solid color. Yeah, we have a couple outliers where the signal's overshooting. There's some reflections here, like the signal's exceeding the main level. But for the most part, it's uniform.
Mm-hmm.
Now I'm going to turn off the system
Mm-hmm.
and let's watch what the signal looks like as the system boots up and it starts initializing and going through the training. You'll see, especially DQ, you'll see that the signal will increase, get smaller, larger, and as it goes larger and higher, that's the ODT sweep process where the system is trying to fine tune the correct ODT. So watch this signal here
Mm-hmm.
as we turn on.
Mm-hmm. It's doing.
Yeah, it's kind of going in and out, trying to get the right timing. I'm gonna start. So it's not, I mean, if we do just a single trigger, it looks like it's not very frequent, right? So the memory controller is definitely not fully active. It's just, in fact, if I set a trigger, set this to channel 2, set the trigger down here, and it's picking up this noise, but it's like very, you get this very infrequent traffic. Notice how these aren't even aligned at all,
Mm-hmm.
right? So that one thing, it's sort of the memory controller saying, "Hey, are you there? Are you there?" It's trying to wake up the memory, but the memories, there's no application running, and so it's just more. I'd call this more of a standby state. It's in an idle, waiting for an application to take over the memory and start using it. That's what we're looking at there. Now let's go ahead and start mem test. And you'll notice a big difference here. Okay,
Mm-hmm.
there we go. Now we're fully trained, and boom, now we're running test modes, and it is working like expected.
Mm-hmm. So when you already mentioned this, first before I forget, basically same measurement would be used for DDR3, DDR4, DDR5. You would measure these 3 signals and have a look on these 3 signals, correct?
Yep, exactly.
Okay.
Yeah, you would in the data sheet or the JEDEC spec, you'll have things like what's the slew rate, what's the VIL, VOL, voltage input low, voltage output low. You may want to measure the clock period, yeah, things like that.
Mm-hmm. But there are easy way how to do it, automated way. But again, before we go there, the second thing what I would like to talk about is the training, because we already mentioned this. So couple of weeks ago, I received an email like, do I need to train my memories on the board? And I think we should explain what is happening during training. So training is important because the system has to figure out how far the memory chips are and how much delay has to be used. At least that's one of the things what is why the training is used, correct? Because there is retraining, write training, and there are a couple of, I think, different things what are actually decided during the training.
Yeah, I think there's the delay optimization time. So there's timing, and then so that's accounting for propagation delay. How long does it take for a write cycle? How long does it take the moment the data is on the wire out of the controller until it arrives into the input of the DRAM, to the latch?
Yeah.
What's the delay one way?
Yeah.
Then there's the intra-pair skew delay, between the data and the strobe, how well time aligned, how well matched are they? So we have to deskew that part.
And also, I think there is timing which has to be find out how far each memory chip is when you access when you are doing address access or something like this.
Yeah, because
Flyby technology can, if you use flyby technology, then all the memory chips are in different distance from the memory controller.
yeah, flyby, for those who are not familiar, DDR3 and earlier used to use a T branch where the clock, for example, would come in, say, near the center of the DIMM. It would get split into two directions, and then it would get split again two separate directions. So you have four and then split again until eventually the clock arrives at into the input of each DRAM. You could have 8 DRAMs, you could have 16, 12, it depends on the configuration. But those, the matching, the timing had to be so tight. And with the speeds getting faster, it just wasn't practical to scale that to higher speeds. So the flyby means that the clock comes into one DRAM and then the signal's picked off, and then it goes to another DRAM, it's picked off, and then it goes to the next one and so forth in kind of like a circle. And the last DRAM in the chain has the termination. But every time we go along, we move from one DRAM to the next, we have to tune the receiver so it doesn't add too much reflection.
Mm-hmm.
So imagine the timing, right? The clock arrives to the first DRAM, could be nanoseconds before the last DRAM gets it. We have to account for that flight time.
Yeah. Okay, so that's why I don't know the exact details, but I know all these timings are set during the training. And my next question, what I would like to talk about is, we use this interposer. Are we not going to damage the signal which is running through the tracks?
Oh, great question. Um, well, like any DDR design, whether you're doing, well, especially if you're doing the PCB layout, you want to make sure that like all the timing is met and the signal loss is not too much, and right, just all the design criteria has to be met. In the same way, when we introduce an interposer into the system, like like this one here, right? We design this fixture so that way it provides good mechanical signal access, but also we make sure the thickness is designed just right to limit insertion loss or other signal degradations. But this, in the same way that a DRAM package is designed to produce minimal loading on the signal, we do the same thing with this interposer. So
Mm-hmm.
mechanically, it's thin, it's small to not disturb the circuit, but electrically also, we've done lots of simulations to make sure that when we put this in the system, the extra load won't cause the system to not work, right? The last thing we want is we want to test it. We insert this module with the interposer in the system, and now it won't boot.
Mm-hmm.
So we've done a lot of studies to make sure that it still works.
So is it possible to buy these interposers?
Absolutely, yeah. Keysight sells these, as well as any number of test equipment company that offers DDR solutions like this would typically have this interposer available.
Mm-hmm.
And they range from, a few $100s to some, like the LPDDR5 interposers with nearly 500 balls. By the way, this is a 78 ball by 8 device with interposer. So 78 balls. The LPDDR5 interposer has nearly 500 balls, and I believe that's a few $1,000s.
Okay. But also, I believe the effect of the interposer and probe can be kind of eliminated if you use like really good oscilloscope.
Yeah. Well, yeah, that's true. High bandwidth oscilloscope to preserve the signal so you're not filtering or loading it down. But equally important are these probes here that we showed connected to the system. The probe amplifier is meant to present a high impedance to the system. And when I say high impedance, at DC, it's 25K or 50K ohm. That's such a high impedance. It's not pulling off a lot of current from the system. So by the way, when we have this, I'll show this one, it's probably a little bit better, but when we have this system connected up, the signal's still going from the PCB, from the controller, up vertically to the DRAM that's on top. But inside this interposer, there's a special trace that taps off part of the signal. So it's like a splitter. So most of the signal is going up to the DRAM, and a small amount is coming out through these probes to the oscilloscope.
Mm-hmm.
And they're designed to not pick off too much of the signal.
Yeah, but I mean, I don't know, I forgot the exact name, how it is done, but I think when you buy this kind of interposer, you also can download the S parameter files or something, and in these very expensive scopes, you can actually eliminate, or you can actually kind of virtually probe exactly the signal on the memory chip and see it, because you can somehow eliminate all the, if you have this S parameter model, you can eliminate all these effects from the interposer and connected probes. Or am I wrong?
You are absolutely correct. That is an excellent memory. Yeah, we talked about this before. That process that you describe of removing the effects of the interposer, because yeah, you will see reflections and non-ideal signaling from just having that connection there. And we call that process de-embedding.
Okay, de-embedding.
So we physically embed the interposer because it has to be there to give us access to the signal, and then virtually through software we can remove that if we know that we have to know what we're removing first. So that's the S parameter. The S parameter is the model of the interposer response, right? And so here's an example of how we would do this.
Can we compare
I'll just show
it?
you
I'm curious, can we compare the signal, how it looks when we do the embedding and without it?
Yeah, let's try that. I'm going to choose channel 2. That's our data. And the software that we use is called Infinisim.
Mm-hmm.
So I'm going to select 2-port. 2-port typically refers to a single-ended signal.
Mm-hmm.
4-port, if I choose 4-port, then that would mean differential.
Mm-hmm.
So I choose setup. And then what usually happens is you start getting into this setup menu. I'm going to create transfer function from model. Now I have another view here. And the nice thing about this, I don't have to create this from scratch. There's different presets or templates.
Mm-hmm.
Here's one that says remove loading effects of a DDR interposer and probe.
Mm-hmm.
Okay, so it sounds like something I want to do. So let's do that. Notice now you have kind of a circuit diagram. And what this is intended to do is to walk you through, please, as a user, I need to then tell the software what my circuit setup is, what driver impedance I have,
Mm-hmm.
what termination I use, do I have any special, voltage divider or other channel definition I want to use. And of course, the red means I need to take action. So if I had an interposer file, I could choose S parameter, and maybe I'm just going to I don't have the interposer loaded into this
So
into the
you don't really
software.
need it for this kind of measurements, do you?
You need the S parameter file of the interposer in order to in order to virtually remove it from the measurement. So I'm just showing you the setup,
Yeah.
but I don't have it available on the scope yet.
Okay. But
So I would do that.
I mean, to test your DDR memories, do you need to do this? Do you need to use this kind of setup, or you can just simply use
Yeah,
it
I mean
without?
it's optional.
It's
A
optional.
lot of
Okay.
yeah, a lot of people will still do this.
Mm-hmm.
You know, as you can see, it's not. It takes time to set it up, and you know, it's if you don't do it right, you could then, as they say, garbage in, garbage out,
Yeah.
right? If I don't have good models coming in, it doesn't matter how good the signal is. It's gonna distort the signal because it's not set up correctly. So
Mm-hmm.
this requires very good attention to detail. But as you say, you know, this is not required.
Okay.
It's common, but not. We could still make measurements
Oh,
without it.
that's really good to know, because I thought you
Yeah.
really need it. I'm very surprised that you can actually connect interposer and probes to very fast signals, and you still measure what is really happening on the
Yeah.
signal. Uh,
Um, one other thing I wanted to show you is remember how I said, you know, you have the read and the write burst.
mm-hmm.
Well, here's I'm going to show you kind of a very common way that people, if they want to isolate the read and write burst on screen,
Mm-hmm.
here's a common way to do this using a trigger setup. So I'm going to trigger on channel 3 because that's our strobe.
Mm-hmm.
And I'm going to choose Infiniscan is like a zone. It's a zone trigger.
Mm-hmm.
Um, so in this case, I can just draw a box like this.
So it's going to trigger only where this big space will be, or something like that.
You can tell it to trigger if it's not in there or if it's in there.
Okay.
Um, but I think we're, okay, sorry.
It has to be
We're zoomed
smaller.
out.
Yeah, that's what
Yeah.
I was thinking about. Yeah.
Okay. So let's kind of zoom in here like this. Okay. I can already tell, you know, if you look at the trace on the bottom, that might be a good way to start. So we have this, but notice that this initial pulse is starting low and sometimes it goes high.
Mm-hmm.
Why do you think it goes high and low like that?
I think that's the difference between read and write, no?
Yeah, exactly. So the polarity is one thing. So why don't we test that theory and say, draw this box and say zone 2, the second one, must intersect.
Okay.
Okay. So now I get the same one every time, but I notice we get one that just kind of pops in there. So I'm going to, just for good measure, or you know what, maybe I'll move this in a little closer.
Mm-hmm.
So that's one thing you notice there. Another thing that's interesting, if I move this back, in fact, I'm going to take this out and I'm going to delete this for now. But I wanted to highlight, I want to show you what these look like together. Okay, I don't know if you could tell this, but there's a smaller amplitude that's riding on top of the larger amplitude.
I can see it,
So
yes.
the larger amplitude would be the read, and the smaller amplitude would be the write. And it's also not very apparent, but the smaller amplitude has a slightly slower rise time, slew rate, because it's going through the channel. DQS and DQ are both bidirectional. Oh, the clock is always from the host,
Okay.
but DQS, DQ, they go in pairs. So DQ is in the middle here, the green one. DQS is blue, channel 3, and they always go together. They're always time aligned. And here's the other interesting part. Notice that DQS starts earlier. It toggles, or it's active earlier than DQ. Why do you think that's the case?
Because when the data are sampled, I don't know.
Okay. It's kind of a trick question. It's a pretty low level behavior as part of the system. I got to get, okay, there's a read because I could tell the signals are rise times faster, but the data doesn't start toggling until 1 or 2 bits after, because this is called the preamble.
Mm-hmm.
Okay, the preamble is like, let's charge up the line, and it's the whole setup and hold thing. We need to set up the strobe, the clock for the data, and have it ready so we can then reliably latch the data in.
Mm-hmm.
Now, if we move this to the right, so if we find one that, go back a little bit more, maybe zoom out a bit. Okay, here we go. This is good. This is perfect. So DQS, our strobe, is toggling before the data starts. The data's latched in, boom, boom, every rising, falling edge, boom. We get that bit, we get that bit, right? So rising, falling, until the very end. Notice that this goes high impedance. And finally, this is high impedance as well for a short time. This always pulls up high. So during the idle state, this is pulled up high here. And then we have to hold this last part. This is called the post-amble, right? So we have to, this is the last latching edge. This goes high, it's done. And then finally, a half a cycle later, this goes high impedance. And then this turns on, and then now we have our data starting up again. So the boundary, the preamble, which is this part right here, and the post-amble, the small part here, is to ensure setup and hold time for the data right here. And we actually have a test for that. We test to make sure this is the right duration.
Okay, so this is what people would be looking for when they would be measuring the signals. They would like to recognize when it's read and write and measure it correctly. But actually, the data signal, it doesn't look so nice.
Yeah, very correct. Yeah, very good. That is not the best data signal for sure. So one of the tools that we have in our software here is equalization, and this will help clean up the signal. And I admit this is a software thing. So
this is not going to clear it physically. This is only going to help us to maybe read some specific values of the bits or something like that.
Yeah. So in the BIOS, as it initializes it and it does the training, like the write leveling and the read training we talked about, another training is sending a special test pattern that allows the memory to kind of set its receiver, and it says, okay, I adjusted the equalizer a certain way, and it sends a signal back. Is this okay? Nope, not good enough. And then it readjusts, and it does this back and forth until it finds the right DFE tap values. The taps are like weights. They're gain coefficients to boost the signal. And in that way, if the signal is small on certain bits and larger on others, it knows, based on the training, it knows that I need to apply more gain to this one and don't touch this bit here. And that's the whole premise of equalization. Equalize means levels are matched across every bit.
But you say this equalization is just the software like here in the scope. It's not going to change the equalization in the memory chips or somewhere.
Correct.
Okay.
If we have access to the mode register settings, we can query or read the final training settings that were applied. And if we can get the DFE tap values from the software training sequence,
Then
read
you
that
can
from
put
our
it here.
system. Exactly. Yeah, that's a
Ah,
lot
okay.
of people do that. They query, they run a report or they query the register values, get those settings, and then you come into this menu
So then
and
you
you
really see what the memory chip sees.
exactly. Yeah, because we can't fit now the interposer allowed us to probe as close to the ball of the DRAM package, right? But the equalizer is inside the package. It's on die.
So we
And
can't
because it's
really
on,
probe behind the
yeah,
equalizer.
yep. So in that way, we're sort of, I guess you could say it's a hybrid measurement and simulation.
Mm-hmm. Okay, but this
Yeah,
is only for DDR5 because DDR4 and 3 they don't have equalization.
correct. DDR4 had equalization, but it
Simple.
was optional,
Okay.
proprietary. DDR5 now standardized and said everybody uses 4-tap DFE. It looks like this, and here are the gain, the tap settings, etc.
Okay.
Um,
So
one more thing,
yeah.
Robert, I want to point out that's kind of important. This signal is really noisy. See the noise on top? We're measuring DDR5 4800. And remember I said 4800 megahertz, megabit per second. The fifth harmonic is about 12 gigahertz. That's the kind of, for that speed, that would be sort of the average bandwidth maybe that I want to use. Typically, it's more like 16 gigahertz, but 12 is sort of the minimum. But here's the bandwidth that we're using for each channel. With these probes are 25 gigahertz.
Mm-hmm.
So we're measuring a lot higher bandwidth. And in that regard, I think we should lower the bandwidth and say maybe we'll go 13 gigahertz. And now look at the signal.
Mm-hmm.
It reduced a lot of that random noise, and it'll look a lot more clear. But we still have this, low signal swing and a lot of jitter and ISI that we have to deal with.
Mm-hmm.
But I
Okay.
think we should. I think we can make measurements.
Okay. That's my next question. So when we are testing memories, we really don't want to measure it manually, or maybe we can measure it manually just to have a look, but because it's so complicated, there are so many measurements, ideally we would like to use a wizard or something, or a tool which will do
Yeah,
all these measurements kind of automatically.
absolutely. Yeah, here's okay, the preamble timing. I want it to be a certain amount of time. I'm going to manually measure the preamble time from the moment actually the ODT turns on typically a little bit after when it starts going low. So here we have 822 picoseconds, which I think is close to 2 clock cycles.
Mm-hmm.
So here's one clock cycle and then 2 clock cycles. So that would be the time that we would measure manually. But is that really the worst case? What about, this one going here? And there's thousands of bursts. We definitely need automation. So that's where here this application here on the right. Now, if you look at my desktop screen that I'm sharing,
Mm-hmm.
I'm remoting into the scope and I'm showing you this. This is the DDR5 app. By the way, I ran this app from this pull down list.
Mm-hmm.
There's a long list of different technologies that I could test to,
Mm-hmm.
USB, PCIe. So I chose the DDR5 app. There's DDR4 and DDR3 as well.
And this would be similar between different oscilloscope manufacturers, I think.
Correct. Yeah.
Yeah.
In any given manufacturer would have a similar list because these are the very common IOs that you see in a digital system.
So how does it work here on Keysight?
Okay, so here's the application that will take us from hours and hours of testing to less than a minute. Okay, it is that easy, trust me. At least once it's set up. So generally you move left to right. Okay, so we have setup, select test. These are the tests that are available.
How do you know which one you need to select?
Oh, good question. So these tests highly depend, the tests that are listed that are available highly depend on the signals that you select and the burst type, and of course the channels that are available. Okay, so if I were to select, let's say,
you don't need to change it because if you change it, then okay.
Okay. No, I was just going to show you. You know,
I understand because if you probe different signals, then you can do different measurements.
Exact clock, right? I don't have clock selected, but if clock were available, I could measure the clock jitter, like how clean is the clock from a timing perspective. I chose miss earlier. Another part that remember the read write separation thing that you know, if I use this, then I can draw a box and say, okay, this is a very specific type of burst. And then if I move this up here, now I'm getting the other burst type, right? I don't want to do this. This is nice for visualization, but when I'm making the specs are based on, there's a spec for the read burst and there's a different set of specs for the write burst. So the software has to be smart enough to be able to determine that. And there's different methods that we use. We can measure the phase offset of the data in the strobe, or if we have the ability to only transmit read or write burst. And I'd say the most reliable method is what we call CA4 burst latency. Okay, meaning we measure the CA signal when it's active. After some time, after some latency, the read and the write burst are then active. And so we have to know.
I remember the table. So the protocol specifies when the read and write is happening, and this A4 signal is important for this. That's what we are talking about.
Yeah, this literally is the read latency.
Yeah. So when this A4 is happening, then it means, I don't know, it's going to be read or write. And then we have to wait because the read and write is not happening immediately after this command is sent. There is some delay between what is happening on address and command bus comparing to what is happening on the data bus.
Exactly. Yeah, good memory. When the CA4 signal is low, it's active low, that corresponds to a write. Okay. And when the CA4, which is shown here, not where my mouse is. Yeah. So, and then when the CA4 signal is high, then that corresponds to a read burst. That's the next burst that comes after the high we're expecting it to be a read. Now, in reality, there are commands that may not correspond, maybe the CA4 is high because it's in an idle state, because the CA4 is pulled up to high. That's the normal bias termination voltage. But for sure, we can predict that the CA4 is low. It's a write. So if it's not a write, well, we assume that the burst is read.
Okay.
And so we have, anyway, we have to put in these values. And so that's one part.
Where do you get
Then,
these values from? Specific
ah,
memory?
yeah, yeah. Oh, great question. Okay. To save time, um, I'm going to show you a setup file that I created recently. Let's say I want to get that for the right. I have a view that looks very similar to, let's see
These
here.
pictures.
Yeah,
Oh, okay.
so here I have, I'll set the cursor at the proper start of the burst.
Mm-hmm.
And then notice that of all the CA4 bits, the one
Mm-hmm.
location where it's
Ah,
always
okay. I
high.
see it. I see it.
So based on this, I know it's 17.6 nanoseconds. Now I have to convert 17.6 nanoseconds to in TCK,
Mm-hmm.
clock cycle. Okay. So that is 42.76 clock cycles.
Mm-hmm.
Okay, and let's do the right first.
This is super
Uh,
useful because I would be probably trying to find these numbers from, I don't know, datasheet or memory controller or something, but it's much better just to measure it this way, then you will be sure what the settings actually really are.
yeah. Okay, now here's another hint. Notice that based on the settings that I have, the right should be, see, I think it's important. Like it's easy to get confused with all these numbers and like what? I have to know exactly the clock cycle. This is confusing. But if you really pay close attention to the diagrams, it kind of tells you what to look for.
Mm-hmm.
So it's color coded. Red is the preamble. And if I change the preamble mode to say a 4 TCK, notice that, whoa, now this red part changes.
Mm-hmm.
So
It
we
has
have
to
to,
look exactly as what you see when you are measuring the
yeah,
signal.
yeah. And so I want to show you something that I think is important. Um, this is a right. This
Mm-hmm.
is supposed to be a right, but um, for some reason, I know that a right is active low, but this is only high. So for some reason, this signal is not matching
Any of these.
how this diagram, right? If I look at the blue signal here, the first pulse is
Up.
rising. So that looks
Yeah.
like a read,
Yes.
which actually is true because a read has is
Up.
a logic
Mm-hmm.
high. So now if I open up, so I think my setup files are named improperly. If I open up the read, and yeah, well, I have to, let me fine tune this here a little bit more.
Yes, I can see it. Yeah.
Okay, there we go. Now it's always low, and there's our latency. It's a little bit different. And instead of 17.6 or whatever it was, now it's 16.8. And that corresponds to 39.11, if I convert the clock cycle that I have. But this is kind of the tool of choice, the setup that you would use to, it took me about 5 minutes. So it's not something, a easy button. It's not quick. 5 minutes, I get this value, then I put it in here. Now, in the future, this is what Keysight is working on. In the future, we'll just automate this, right? We're a test and measurement company. We automate measurements, but we created this initially based on reading the spec. And so in the near future, this whole process will just measure these
Mm-hmm.
values and automatically detect that.
Mm-hmm.
In fact, Robert, honestly, this is AI waiting to happen. This whole, we have so much data here. we can just process this into a machine learning algorithm and say a burst looks like this, or a read looks like this, a write looks like that. And then once we do our training, then we can give it any signal and it should be able to quickly detect. So that's
Yeah,
where we're
if the
going.
signal is not like really very weird.
Yep, exactly. Exactly.
Then it would say something like, oh, I'm
Like,
10% sure this is right.
yeah, exactly. Like, well, we think it's this, but we're not quite sure.
Okay.
Okay, so that's that setup. Notice here I have also the channel assignments. I have the signal name with the given channel number. And then also part of the setup is we need to know the thresholds for how to detect. And there's this nice little diagram that shows, you know, the lower threshold should be below the electrical idle and the upper threshold should be above that. And so sort of like the termination level could be the middle. So we have to do that for each one. And this is very common. Every scope company has a menu that looks like this. And so normally, you know, as a user, if I'm first starting out, I would probably turn on markers, you know, the lines on the scope screen,
and have a look
and I would come in here and
when the trigger works the best.
yep, exactly. I'd say, okay, the signals, oh, you know, I'd move the marker there, and I would use the vertical levels because I need millivolt, right? I need to come in here and get these numbers and then put those into here. Now, again, this is also begging for automation, but yeah, so we're getting there. But anyway, that's that one. Let's go ahead and move to the test. Based on the DQS, DQCA, here are the signals for the read and write burst that I can measure. So we have the time for the read preamble, time read postamble, output.
You can just select
low.
some of them or all of them. I don't know which are going to fail or pass.
So some of these will fail because of the way we're probing, but you know, why don't we just run them all and then we'll see.
Okay.
We'll see what that looks like. Okay, so here's the connection, you know, little diagram. It's reminding me, hey, don't forget channel 1 DQS.
Channel 3.
Yep. Okay, so you start running here and it gives you kind of a message, a status here below. Well, I like to jump to the results panel. That way, as the tests finish, you know, the results are populated here and I can kind of see, oh, you know what? And also the
you need to run the memory test.
Yeah, restart that so we have some good signals. Okay, so the first test ran. The read preamble is here. And you always want to kind of you want to do a sanity check, right? The software will just give you a number. How do you know it's correct? I do remember from the earlier setup, the initial pulse for the read was positive, and the you know, the write had a negative going pulse. So you want to look at these results and kind of, I guess, fact check to make sure it's what you expect.
I know someone told me once, like, you may notice if by mistake you swap, for example, negative and positive signals on probe, then it may not.
Oh, yeah. Yeah, actually, you know, we should do that just for fun.
No, don't do it.
No,
We will
like,
not have time for it, but I would like to see how many tests is going to fail.
Well, here's already a test that failed, not because of a bad signal, but because we didn't get the right signal. And that's where the burst separation comes in. So I'm very confident that there was a burst separation problem. In fact, here, I'll go up here. See this result? It's like very, very large number. And you look at the screenshot and there's no signal.
Mm-hmm.
Well, of course, the result is completely wrong.
Mm-hmm.
And so we would need to go back and look at why did the B output high, why did that not capture the signal right? Well, I'd say in my experience, 80-90% of the time, it's because of the threshold setting that I used
Mm-hmm.
in the setup. I would need to fine tune that a little bit
Mm-hmm.
more. And but anyway, we've got some more results here.
Yeah, so what are these? I'm curious.
So SR is slew rate, Q is the DQ, and SE is single-ended, and then R is for rising, and F is for falling. And it kind of makes sense if you think about it. Look at every edge, give me the worst case slew rate. And it actually found it. Look at how slow this edge is. This could be a problem.
But
And the
this could be
rising
caused
edge,
also because we use the interposer and connected probes.
exactly. Yeah, that's a really good point. And if I were to de-embed the interposer, I can guarantee the slew rate will be the rise time will be faster, and this slew rate would be much better.
Mm-hmm. So
I
basically, we just
definitely,
need to have a look on these numbers, for example, how far they are from the tolerance, and maybe if it's very close to the tolerance, we can consider them still okay.
yep. Yeah, in fact, that's another useful tip is, I mean, it's one thing to get the actual value, but I like how, we provide the spec limit, the pass fail.
Yeah,
In this
that's
case,
useful.
it's a
Yeah.
range. And then we report how close were you to the spec limit. So in terms of margin. Now, I don't remember what the threshold is, but red means you're really far away. If you're really close but failing, we say yellow. Like, oh yeah, there's a pass. This is a
Mm-hmm.
pass,
But it's
but
close to the.
you're really
Mm-hmm.
close.
I see.
So I think we're already into this nearly 5 minutes, right?
No, I don't know.
Something like that. But
Yeah, it
we
says
got quite a
9:26:37. Yeah, 5 minutes. We are running 5 minutes.
yeah, we've got quite a few results here that we can, start analyzing or using.
Okay, indeed.
Yep. Yeah. So and then of course our report, we have the software name, the version, kind of the setup information. This is like a header. I use these probes. So if somebody says, well, which probes did you use? Oh, they're not calibrated. So, hey, that's maybe something we want to think about. I just got these in recently and didn't even calibrate them.
Mm-hmm.
So maybe I should look at that. Summary table and kind of at a glance. These are hyperlinked. So I click on any of these and it jumps to the either one. Go back to the top, get one that passed. Okay, this looks well behaved. There's a little bit of reflection here, but it's for this slew rate test, it looks fairly reasonable. How about let's look at one of those preamble.
This is very interesting because I remember when doing memory simulations, it's very similar. Like when I run all the tests in memory simulation, some of them will always fail.
Yeah.
And you just have to find out why they're failing. If you really need these tests, or they're failing because something is really wrong, or if the setup is wrong, or it's like really something bad.
Yeah. Yep.
Okay, Randy, I asked all the questions what I wanted to ask. This was really cool to see how actually we can measure system, we can probe memories, because that's like very important. And now I know what kind of signals I should probe and where to start. So thank you very much for helping me to understand this.
You're welcome. Thank you for joining. And it was fun walking through the setup and seeing the measurements and what could go wrong and how to fix it.
Thank you. And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our Fedevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.